everybody. My name is Alaa Mahmoud. I'm a developer at IBM. I work on IBM Graph, so together with a lot of other lovely people who are wearing the same shirt, which is available at the booth if you're interested. So again, I wasn't really sure about the kind of audience that I'm going to have. So the presentation is going to be pretty much like Massachusetts weather, right? If you don't like it, just wait a few minutes. Right? It's going to change. So we're going to talk a little bit about Graph. We're going to talk a little bit about the cloud, and we're going to talk a little bit about also about IBM Graph as well. So graphs are really cool. They're the natural way to store and to query data in general. They love complexity, and at the same time, they make you focus on the problem and not the data model. Let's start with, whenever you're trying to kind of model your data, you start with the state-of-the-art data modeling tool, and that is the dinner napkin, right? So the dinner napkin is the traditional way of representing your data. You have your entities, a product, for example, in this example that I have, which is a typical retail data model. You have a product. This product would be bought by a customer. The product is offered by a seller. The relationship between all of this, you have a product that is being offered by a seller. A customer buys the product. A customer can rate a product. A customer can rate a seller. Right? So this is kind of the data model that we're starting with. In a traditional kind of RDBMS thing, you would start by looking at this model, and you would say, well, I have a product. I need a table for this product. I have a customer, so I'm going to create also another table for that customer. I also have a seller, so I'm going to create another table for that seller. But I also have relationships. So I have a relationship between the customer, between the product and the seller, so I'm going to create an offer table that links the two. I'm also going to create a rates table that will allow me to kind of see the customers who are rating products or sellers. I'm also going to have a buys table that will basically tell me which customer bought which product. By the time that you're done with this, that mental model, that beautiful mental model that kind of told you how the relationship, how the products, how everything kind of work together is no longer in the picture. Right? When you're working with a graph database, you start with the same model, the entities and the relationships, and then you model them, and they look exactly the same. Nothing changes. And even if that napkin kind of no longer there, which I hope it does, because it's not going to last for a long time, you still have that really beautiful model that tells you the relationship between the entities and the things that you have. So the other thing that is really cool about graph databases in general is that they no longer need joins. When you're dealing with SQL, you have relationships. You know the joins hell, right? You have data all over the place. You need to join the data in order to kind of understand, kind of get an insight to these relationships, and it can be really, really tedious, especially if you have a lot of entities and a lot of tables that are relating all of those entities. With something like Gremlin, which is the Tinkerpop equivalent or the Tinkerpop query language, it's much, much more simpler. It's one statement that tells you exactly what we're trying to do. It's almost self-explanatory. In this one, for example, we're looking for customers. I'm following all of the orders that these customers made. I'm just going to get the customer name, and I'm going to also get the order date for those customers. It's much more simpler, no need for joins. There are hurdles that affect graph databases. And the hurdles are, graph databases are new. It's kind of hard for a company, for a CIO, for a CTO, for somebody who's trying to kind of put together a solution to find experts in the field. A lot of people think that graphs are charts. They are not. A lot of people, when I tell them I do IBM Graph, oh yeah, that's really cool because I really want to store all my charts somewhere. Like, that's not what we do. There are lots of pieces. It's not really a single piece. It's not something that you go and you download and I'm done. No, it's a lot of pieces. This is kind of one of the very popular graph databases that are out there, Titan. This is not a typical Titan architecture, but at least 2/3 of what you see on the screen will be on any deployment that you're going to have. And you're going to have to maintain all of this. So for somebody who's trying out Graph for the first time, thinking that I really need to do all of this in order to just try it out, while I know SQL very well, I know Mongo very well, I'm going to stick with the things that I have. Like any other distributed system, as I said, they required a lot of maintenance, and somebody had to do that type of work. Cloud comes to the rescue, our hero, right? So cloud allows you to concentrate on the problem, on the software itself, right? Graph in this case, and not on the administration, not on setting up clusters, and not on setting up and configuring software and so on and so forth. So this is kind of really the beauty of the cloud, is that it makes you to kind of do this type of thing. It's available. One of the things that cloud has is redundancy. Anybody who implements a cloud solution implements a lot of redundancy. You don't really have one server, you don't have two, you have multiple servers. The data is replicated across multiple pods, across multiple data centers, and so on and so forth. No matter what happens, one of these entities will be able to kind of serve the queries, serve the data that the person has as well. The issue that we hear a lot about people coming talking to us about Graph is, I don't really know how much data I need. I want to be able to start with one particular size, but I want to be able to scale. In any software, if you want to scale, you want to have, you've already bought certain hardware, you want to buy different hardware, you want to increase your memory, you want to increase your disk space, you want to create other clusters and so on. With the cloud, that happens automatically. It's kind of hidden from the user. It's cost effective for both, for enterprise, for startups who don't really want to spend a lot of money because they have a limited venture capital money that they're dealing with. With the cloud, they can start small and they can pay for that small size cluster that they have started with, and that they can grow with their product. So the more customers, the more users that they have for their product, the more money they get, then they can pay more money and they can grow from being a startup into being an enterprise afterwards. It delays your commitment. When you're talking about any software product that you have to buy, you're buying hardware, you're buying software, you're hiring people in order to administer your clusters and so on. You don't really need to do that with the cloud. It delays your commitment. You can try out, you can play with things, and once you're convinced that this is the right solution for you, you can opt in if you want, without having to invest quite a bit. People, a lot of times, are actually worried about data centers and the security of the data centers. When you think about the people who are administering the data centers, the expertise that are looking at the security of the data centers and so on, they're definitely much more secure than the server room down the hall. The cloud is effective for like two reasons, probably multiple reasons, but I'm going to mention two of them. And one of them is sharing. I'm going to say a little bit what sharing means. The other one is automation. This is a terrible example that I'm going to give, so I'm going to admit it's a terrible example, but it kind of gets the point across. If we have four people who need a vehicle, right? They want to go to work, they want to drive their kids to their soccer practice and so on and so forth. Each one of those people can buy a compact car. They're going to pay full price for each one of those compact cars. But the car is sitting idle most of the time. They drive it to work, the car is sitting out there. Most of the time, 4 of the 5 seats are not really used. If these 4 people can trade this in and instead share a much bigger vehicle, much more luxurious vehicle with a lot of bells and whistles, it's a much better utilization of the money that is spent. And the money that will be spent by these 4 or 5 individuals will be less than the amount of money that they will be spending in order to kind of use or share that kind of luxury vehicle and so on. So that's kind of where sharing works. Because in the cloud, a lot of the time, the cloud providers, we have huge clusters, huge hardware. But what makes it work is that a lot of people are using that same hardware together. And we have much better utilization than the hardware that is being used by individual companies. But when you're hosting, what to host? So one of the things that kind of, when we're thinking about when we thought about hosting a graph database is what to host. We didn't want to host anything that's proprietary. Yeah, I work for IBM, but we didn't want to host anything that is proprietary. It's surprising, but it is the truth. We wanted to host something that is open source, and we wanted to host something that is based on standards. There's a reason for all of this, right? It's when you host something that is open source, you get the whole community contributing to it. No matter how great your software is, there's a limited number of people working on it. When you have an open source product, when you have an open standards product, you have the whole world working on it. You have people in Japan, you have people in China, you have people in the US, you have people in Europe. Throughout the world, there are people working on this product and adding to it. So open source, open standard was the two things that we wanted to make sure that we have. So we settled on a very popular graph compute engine, Tinkerpop. It's an Apache project, and I'm sure you probably heard that name quite a bit today, especially from Jason. But it's a very, very active community of very smart people working for very known companies. Most of them have graph solutions that they're offering. So they're contributing to this open source with as part of their work. A lot of them actually, part of their work is to develop the software and contributing it back to the community. So we used Tinkerpop as what we're going to be hosting. And at the same time, what we're getting from Apache Tinkerpop is that it is very popular and is used by actually multiple of the offerings that you see right now. So things like, DSE Graph and others are actually using Tinkerpop under the hood. And that enabled us to do a couple of things. One is that people who are already familiar with Tinkerpop, with the Tinkerpop ecosystem, they can easily move into IBM Graph. So they understand the query language, they understand the infrastructure, and so on. But at the same time, even people who choose IBM Graph, whether to try it out, to learn Graph, or to even use it, and they decide to go somewhere else, they have that freedom of movement. They're not really stuck with us or with anybody else. So that's kind of the beauty of open standards and open source. There are lots of cloud challenges. What to offer? So when we talk about what to offer, we could offer a multi-tenant instance. I'm going to mention what that exactly is. Or we can have an instance for each user. Shared multi-tenant instance is something that looks exactly like this. We have a huge cluster, or multiple clusters, that basically that is sharing one compute cluster and one compute store. So everything is stored under the same infrastructure. There's no separation per se when it comes to the resources. But at the same time, each and every user has a graph ID. And that graph ID gets authorized. The user gets authenticated first. The graph ID gets authorized, that the user has access to this graph ID. All the data that the user has inside of our store is stamped with that graph ID. So no user can have any access to any other graph but the graphs that they're authorized, that they have created themselves. So all of the users will come into our HTTP layer. Our HTTP layer will be using the standard Tinkerpop implementation, and then we will basically use the graph data that they need behind the scenes. And as it's secure, and it's not just secure. It's actually it's more kind of cost effective for the cloud providers because it has a lot less overhead. It's one cluster that we can will allow us to kind of serve all the users while keeping the cost down and offer a much better service. A slight variation on this multi-tenant service is something that Tinkerpop itself provides, and that is something what they call a partition graph. And in partition graph, you can create one big graph, and from within that particular graph, you can partition it into smaller partitions, and you can assign each one of your users a single partition. So every user that comes in, they have a graph ID or whatever, or even a username, whatever you decide to be the key that you're going to use. You convert that graph ID into a partition ID or a partition key, and then all the queries and everything that gets executed from that point on basically uses or operates on that particular partition. No user sees any other user's data. One of our customers, at least that I can think of, actually uses that to provide a multi-tenant service on top of our multi-tenant service. So they have one instance that they host on IBM Graph, and from within that instance that they host, they have users that use their service, and they create a separate partition for each one of those. So this is kind of you can have a hierarchy of multi-tenancy on that offering. So this is something that we support right now. The other option, and that is to create those quote-unquote virtual silos. right? So anybody who's familiar with something like Docker or something like IBM Compose that allow you to create very light virtual machines, not the kind of the traditional VMware type of machines, a very light VM that each and every user has the full stack. So instead of having just one stack serving all of the users, you can also have each user have the full stack. This has a little bit of overhead, just a little, because you would have to kind of replicate that same stack for each and every user that you're hosting. But it's much easier when it comes to administration, because every user is an individual. Every user is kind of like bound by how much they can execute and how much disk space and memory they're allocated. So it's much easier for the cloud provider to provide such a solution than the two ones that I've mentioned before. So these are kind of three of the variation that you're going to see when it comes to multi-tenant services that are out there. With the first solution that I mentioned, where like a lot of people multi-tenant across the same service, you get some of the issues that you see is a noisy neighbor problem. Very famous for anybody who's kind of done cloud before. And with noisy neighbor, you have one particular user or multiple that are pretty much hogging the system. These are people who are will execute queries that are extremely complex, queries that are will take a long time. They're going to be accessing the disk more than anybody else. And when that happens, because all of them are sharing the same resources, is that some of the users will be experiencing a much poorer experience than others. So, and when I'm talking about resources, I'm talking about CPU, disk, network, and memory, and so on. There's various ways of solving those, and some of them, can be like throttling. For example, there are resource management that we can do. So with lots of schemes that we have taken to make sure that this noisy neighbor problem doesn't really happen with our users. Everybody gets a fair share of the resources that are available to all of them. The other problem with the cloud also, because with multi-tenancy is that it's very hard to kind of know how much resources will a particular query take. Even a simple query like the one that you have like in the bottom, g.v. This is in Gremlin that brings back all of the vertices that you have. So if you have a billion vertices in your graph, this simple query will bring a billion elements in just one call. So this is kind of like select star.star from like all the tables that you have while joining them. So it's kind of hard. It's unpredictable, and that's one of the kind of very complex kind of problems that it's very hard to resolve when it comes to graph queries. They can be very unpredictable. With the siloed model that we mentioned, each user is assigned a CPU kind of slice. So no matter, even if their queries kind of take up even more time, it doesn't really matter because they're going to be operating within the assigned CPU and disk and memory usage that they are allowed to. So they're not going to be affecting anybody else. A little bit about the team, and I think it's really important, from to kind of understand how we, develop the service. Traditionally, cloud teams would have, or development teams in general, not just cloud teams. There's usually this wall between developers and everybody else. You have advocacy team, you have a development team, you have a DevOps team, and this is probably maybe the biggest thing when that is specific to cloud, DevOps, right? You have a DevOps team that is operating the service, and you have a dev team. The dev team develops the features, throw it over the wall to the ops team. Ops team is trying to operate it. Of course, they don't really know the code as much as the dev team. They throw it back at them when they really can't resolve it, and you kind of see this kind of back and forth between those two teams, and it doesn't really work. And it really creates a very poor experience. And one of the things that we had to kind of fight with, even with with the traditional kind of managers that we had, it's no longer a problem, but it's used to, we don't want that. What we want is, and what we ended up having is just one big team. Everybody does everything. So our team basically does the development. Our team does the QA, our team does advocacy, like what I'm doing right now, and we do ops. We all have pages on the weekend and at night. So it's the same team that does all of that stuff. So we know what the problems are. We're the ones who are fixing the problem. And that created a very agile team, but I mean a true agile, not just within, you know, the kind of the you know, it's not a term, it's actually true. In order to keep all of this running, when you have tons and tons of servers that are running, lots of things that could happen to them, you really can deal with server failures and having to solve them while customers are executing queries that are crucial to their business. So what we've done is we've done a very extensive kind of monitoring system where we're collecting data throughout the day, 24 hours. Data is being collected, all sorts of data, CPU data, different kind of metrics about the users, garbage collection metrics, everything that we really need to collect about the servers, about the software that is running, about the operating system is being collected and being stored. And at the same time, there are other processes that are monitoring this. And when certain thresholds are being met, pages are being fired to people who are on duty to kind of make sure that this situation is resolved before it turns into a situation that has to be you know, catastrophic, where we have to reboot servers and things like that. At the same time, we also have systems that are making sure that not just that the servers are running, but also that the servers are actually able to perform all of these processes, like, for example, like making queries, creating data, and so on and so forth. And all of these are basically running all the time. And we have basically people that are on duty that can take care of that. The other thing that the cloud also brought us that we didn't really have before, and I've been around for quite some time, so I've seen the traditional way of delivering software that we don't really have to do in the cloud anymore. And that's really, to me, that's one of the biggest advantages of having a cloud solution. I know of somebody, actually several people, who used to make money off of installing patches for companies. So that was his role. He said, yeah, I mean, people used to hire me to install patches. I used to be a developer on Lotus Notes, if anybody knows that product or remembers that name. So, and I was talking to one of our consultants, and he said, yeah, I get hired by people to actually install. So thank you very much for making the process so complicated. So people used to make money out of this. With the cloud, we don't really need to do that. You know, one of the things that we're seeing on a day-to-day basis, we discover the problems, we'll fix the problems, we test them, we put them on multiple environments. So the minute that a developer, you know, checks some code, we have, you know, peer reviews, we have builds, we have tests, and once it gets tested, it gets deployed into a development environment. If it passes that, it goes installed, you know, on a staging environment. If it passes that, then it eventually goes into production. That doesn't take a long time. That takes, you know, sometimes days, maybe a little bit longer, depending on what we're deploying. But the idea of continuous delivery, continuous deployment, actually is a great advantage of the cloud, where you're always guaranteed to have the latest software, you're always guaranteed to have the latest bug fixes and patches, both on the software itself and the machines and the operating system. So that's kind of one of the really advantages that we had by having this continuous delivery system. All of this kind of seems to be a lot, right? So, you know, you're having pages coming in, you're having code reviews, you're having pull requests, you're having pager duties, builds, Stack Overflow questions. All of that stuff is our team, and and for the team to be able to handle all of this, we managed to kind of create integrations within something called Slack, so that by living within Slack, we get notified by all of this stuff, and we can respond to this extremely quickly. And the whole team basically is overseeing this and is responding to these things as they come in. And I think it's demo time. So I'm going to give you a quick demo to see. I want to show you basically what is the end result. So what happened. So IBM Graph basically is a service that's available on Bluemix. So if you go to bluemix.net, you'll get into this this UI. You click on the catalog, and it'll bring you to this particular page. And what I'm going to do is I'm going to look for IBM Graph. I'm going to create an instance of IBM Graph. So let me create a graph day 2017. So this is the name of the instance. So I'm going to create it. And right down here, you can actually see the pricing and all that. That's for the service. There's actually almost like a free tier, so you can use it up to 500 megabytes and 25,000 API calls per month without having to pay any money. So that's pretty cool. Once you do that, you get what we call a service credentials, which is basically an API call, a URL, and a username and a password. With that API URL and the username and password, you can basically make queries. You can start instantiating graphs. You can start adding data. You can start running Gremlin queries, which we're going to see in a minute. If I go back to the management part and click the open, we've created this UI that allows you, it's kind of your starting portal. This is the portal where you can start, working with the service. And it's really cool for even people who are new to Graph. So even if you're not really interested in kind of IBM Graph as a service, you can actually go there to learn about Graph. So we have these tutorials that take you from an introduction to Graph, what a graph is, and all that. If you're like not familiar, or if you know somebody who is not familiar with Graph, to how you can model your graph and how you can create a schema and so on, and it takes you all the way to creating CRUD, and eventually how to kind of create traversals and how you can create a Gremlin query and getting data out of your graph. But the other really cool thing that you can get from this is sample data, which is very easy to kind of to do with IBM Graph. So if you're not familiar with Graph or you want to play with it a little bit, we have sample data, a music festival data that we have put together, and you can load by hitting the load button. And once this loads, you can also start seeing what we call a query card. And this has some sample queries. So if you're not familiar with Graph and you really don't really know what to do, and you don't really want to read like pages and pages and volumes of documentation, you can look at this sample data. So this is the model that we have created, which is basically it's a music festival. It has attendees, it has bands, and it has venues. It has attendees buy tickets for bands. Bands perform at venues, and venues get advertised to attendees. So these are kind of the relationship that we have in our kind of simple graph that we've included. And the sample queries that we have range from CRUD queries. So this query basically creates two vertices, creates two entities, and creates an edge between these two entities. If you hit the arrow, this query gets executed, and you get the results in JSON. So for the app developers, they can actually see on the spot the JSON that gets back from the API call. I'm going to minimize this, and then I'm going to take a look at another type of query, which is a query that lists performances for a particular attendee, in this case like Jane Doe, and you can get the list of bands that she bought, or performances that she bought tickets for. You can also get visualizations. Again, they're not really intended to be your very complex, 60,000, 10,000 vertex visualizations yet, but we kind of defer that to people who actually do that, like keylines, for example. But you can visualize the queries, and you can get simple visualizations of the results of the query that we have. So this is basically a query that says, give me all the bands that have a genre of folk music they're performing at, and get me all the venues. So you can see basically on the screen, you see every venue and all the bands that are performing at that particular venue. And by clicking each one of those vertices, you can see the actual data that corresponds to that particular vertex and so on. So it's a really nice way to kind of play around with the queries. I can actually go and I can change some of them. So I'm going to change folk to hip hop, and then you get the hip hop bands and where they are performing at. And at the same time, you can, through that UI, you can create graphs. So you're not really limited to one particular graph. So you can actually experiment with different things. So let's say that you have different models for your problem that you're trying to address. You can create multiple graphs. I'm going to create another music 1 or music 2, and then I can it's not nice, so I can have space. And now I have another graph, and I can load the sample data onto that graph, or I can load a different data set into that graph from within the UI, and I can play with it, and I can compare the two models and how they perform, and so on. The documentation that we have, this is kind of the API reference, so it's an HTTP API, which is very easy to use, especially from pretty much any language. So if you're building a mobile app, it's easy to kind of call HTTP APIs. If you're building a website, it's easy to create HTTP APIs. And if you're creating, even like backend applications, so it's easy to kind of use HTTP APIs. And also we have code samples for like Node and Java and client libraries and things like that. So this is kind of what we've built, and it's as you can see, like in minutes, we were able to create a graph database. We loaded data, and we started querying the data without having to kind of point to here's the URL, this is what you install, here's how you can configure it, and so on and so forth. It's like in minutes you're up and running, and if you're really interested in graph, this is definitely kind of the best way to start. I'm going back to the presentation, and these are some resources for people who are interested. So if you're interested in IBM Graph, there's a short URL that we have created, IBM-biz/IBM-graph. And also we have a public Slack channel for people if they have any questions, or if you're having any issues, you can always go and we'll be happy to kind of help you over there. And this is a link to the the Apache Tinkerpop for more information. And that's what I have. Maybe we can open up the floor for questions if there are any. Everything is IBM confidential. So one of the really good examples that we have that uses IBM Graph is and I think it's okay to kind of mention their name. If they're not, then I'll be shot later. But the Watson cybersecurity team, which is a major kind of security product that IBM has, actually uses IBM Graph in order to model their if you're into security, all the observables, the URLs, the IPs, all of the data that they collect is actually modeled as a graph from within on IBM Graph, and they have several billion graph elements, and yeah, they've been doing pretty good. So Cypher, we haven't really supported Cypher yet. So currently we're only supporting Gremlin, and depending on how demand is, we may be supporting Cypher in the future. But no plans so far. Yeah. So the multi-tenant one. This is the one that we have right now. But we're also looking into other options. Which client are you referring to? Oh no, these are just sample. No, this is it's a sample Java code that basically makes HTTP calls to the service and brings it back. It's not underneath the covers. It's all Tinkerpop. It's the standard Tinkerpop Java application. But yeah, what we did was we created a few client libraries for Node, for Python. I think there's one that is being done for Java as well to make it a lot easier for people to just instantiate a graph and then start, kind of calling Gremlin right away without having to kind of worry about the HTTP and HTTP calls and all that stuff. So make it a lot easier for people to kind of work with the service. Okay, cool. Thank you so much.